my work here. And so what I'm going to talk about today is the elusive connection between structure and dynamics in supercooled liquid. The word elusive is very elusive, but I guess you will understand why I call it an elusive connection as I will get along with the talk. Why do I talk about it as an elusive connection? So first, let me acknowledge the collaborators. I do work with many people in collaboration. One of them is Shimon sitting there at SN Bose. For this particular work, like I'm going to present a series of work which started around 2013. There has been collaboration with Professor Shrikant Shastri, Professor Chandan Das Gupta, Professor Shiladita Sen Gupta, and recently we are working with Andrew Liu in University of Pennsylvania. The work was done, the first part of the work was done by Dr. Athray Banerjee, who is right now in Max Planck Institute in Mainz. Then Dr. Manoj Kumar Nandi, and the present part of the work is being done by Mohit Sharma, who is a present student at NCL in my group. Now, to tell you what is supercooled liquid, because this is not something very commonly, like especially for the students, you don't hear about the word supercooled liquid much probably when you're doing your masters. The reason is it's not a regular liquid. What do we mean by supercooled liquid? I will just try to explain it before I go into the details of the work that I'm going to present. So supercooled liquid is like when you cool a liquid, normally what happens is we know that at melting temperature, it undergoes crystallization. And that is like Tm. There is a large change in volume and enthalpy, and this is a first order transition. There is a crystallization process after that. Now, when you cool a liquid fast enough so that it can avoid its crystallization, then it enters a supercooled liquid domain, and further cooling it leads to at some temperature it undergoes a glass transition, and I'll come to this what it means here. And if depending on the rate of cooling, if you cool it faster, the glass transition can happen at a higher temperature. If you cool it slowly, the glass transition happens at a lower temperature. And this glass transition is not a thermodynamic transition, it's a kinetic transition. Now, what I told you is I told you supercooled liquid, and then I introduced it to glass and glass transition. So what do we mean by glass? Now, by glass, we definitely mean, it is definitely what you think about, like this ancient glasses are the glass I'm talking about. And we know that this glass making was known for like thousands of years. The earliest glass making was 3600 BC, and it has been depicted in many old civilizations, pictures like how the glass was made. So you must be wondering, something which is about more than 5000 years old, like people knew how to make it, do it, like why is it still something interesting to study? Now, to quote Phil Anderson, a Nobel Prize winning physicist, he said that the deepest and most interesting unsolved problem in the solid state theory is probably the theory of the nature of glass and the glass transition. So, and he expected that probably in a decade we will be able to figure out what it is, but we are still questioning. Of course, our understanding, we are improving it, but it's like when I go through it, you will understand why it is so difficult to understand the system, and the year 2022 has been as a United Nations has declared it as International Year of Glass for both scientific, economic, and cultural role of glass. So no, it's an interesting topic, and it has some relevance in many areas. So that's the reason it's been promoted as an International Year of Glass. Now, by glass, we not only mean those artifacts that I have shown you a few slides back, but all these materials on this slide is glass to us. And why so? You would have never thought a chocolate and a toothpaste would be put on the same slide saying that they share same properties. If you think about it, and here is a gel, here is a colloidal suspension, which can be, your milk, and then here these are pearl pet, like this poly A bottles, like all of them are glass. Now, what is so common in these systems are that, what is common is that all of them show a phenomenal rise in viscosity. So initially at higher temperature, the viscosity is low, and suddenly you will see a sharp rise in viscosity. And when the viscosity is around 10 to the power 13 Poisson, or the relaxation time of the system is 100 seconds, that is when it is considered to be a glass transition temperature. Now, why do we stop at 10 to the power 13 Poisson? Because what you understand from here is this is something the community decided that it is 10 to the power 13 Poisson when the glass transition happens. So to understand how difficult it is to do experiments when the viscosity goes beyond this, I'll just give you an example of the slowest experiment in the world, which is the pitch drop experiment. It was like there are few pitch drop experiments, and by the way, bitumen, which is pitch, is also a glass in our language. So so you will find that this was set up in 1927. First 3 years it took for setting up, then cutting the beaker, and that till last 90 years only 9 drops fell from here. And the viscosity is still not 10 to the power 13 Poisson, it's less than that. So anything which is 10 to the power 13 Poisson, you cannot study a relaxation process there, you cannot do any study. And that's the reason it's called a laboratory glass transition temperature, and it has been accepted that that is what should be the glass transition temperature for the system. Now, I'll give you a brief overview of supercooled liquids before I go into the problem. Now, what are the properties? Do they behave like liquid? Or why are they called supercooled liquids and not liquids in general? What are the different properties? How they are different from a liquid? How they are similar to a liquid? I'm going to tell you those. Now, what happens in the supercooled liquid domain is that the displacement of the particle in the liquid as a displacement of a particle is continuous, but in a supercooled liquid domain you will find a discontinuity in the displacement. Like the particle will be stuck somewhere, then it will move, then it will again get stuck. So there's kind of an intermittency in the dynamics of the system, and this intermittency in the dynamics gives rise to a two-step relaxation process. So what I've calculated, what I've shown here is a very, like, you can calculate dynamics in many ways, you can calculate many properties. The simplest would be to understand the displacement of a particle from its time at time t equal to 0, how the system has displaced, or how the particle has displaced. Now what happens usually at high temperature, this if you plot this function, it is an exponential function. But at lower temperature, it starts developing, after a short decay, it starts developing a plateau and then decays, and this plateau becomes wider. So the longer a particle is stuck in its cage, the wider the plateau becomes. And what happens is, I have plotted only at low temperature, but usually there is a plateau like this, there is a decay, that the plateau becomes longer and longer as you go to lower and lower temperature. So this intermittent dynamics is connected to the caging of the particle. That means a particle will have a vibrational motion within its cage, and then it will have a relaxation, the cage will relax. And when there is a decoupling between the short and the long time dynamics, that is when this caging, that is when this plateau comes up, and there is a clear caging. Now, there is also another property of the system, that is the heterogeneity of the dynamics. And what by that what we mean is, here is a system, the colors, the smaller and bigger particles are not really their sizes, but depending on their activity, their size has been depicted in the picture. So the ones which are more active are depicted in a bigger size, and the ones which are less active are depicted by a smaller size. Now what happens is that as you go to lower and lower temperature, there are this fast and slow domains which develop in the system, and the fast domains and the slow domains, these domains become bigger and bigger, and there is a correlation length which grows with the system. So in a domain, the particles kind of have a correlated motion, but it is still a question. We do not know what gives rise to the dynamic heterogeneity. Why does suddenly the system start behaving in a heterogeneous manner, which usually never happens in a liquid where everything is homogeneous. Every particle you take, you do an averaging over a certain period of time, you will find it will give you same property, which is not in the case in supercooled liquid. And this thing becomes more and more prominent as you go to lower and lower temperature of the system. Now, this heterogeneity in the dynamics also leads to certain other behavior, like there is a breakdown of Stokes-Einstein relationship. So usually in high temperature, the diffusion the viscosity follows the diffusion follows the viscosity, and it can be written by this formula like this, which is called the Stokes-Einstein relationship. But at lower temperature, when there is this decoupling and when there is this growth of domain, then there is a decoupling of the Stokes-Einstein relationship. Viscosity is dominated by the slower domains, whereas diffusion gets dominated by the faster domains. Now also this relaxation, which is exponential at high temperatures, becomes highly non-exponential. The reason this non-exponentiality comes is because particles start behaving very differently, and every particle, like even if each of them have exponential dynamics, when you add them up and make an average, then eventually you will find a non-exponential dynamics in the system. Now, there is also another way of looking at a glass, which is a thermodynamic picture. So there is an energy landscape, which is basically like, there are minimas in the system, and what happens at high temperature, the system doesn't explode this minima, doesn't feel that there is a minima, maxima, these things. But as the system goes to lower and lower temperature, then you will see that there is this minima which becomes like, the system is stuck in a minima, then the system takes a very long time to come out of the minima. So there is this like these underlying energy landscape starts dominating the dynamics. Now, what are these minimas? They are usually called as configurational entropy of the system. So the total, the idea is that if a system is in this minima, then it will only vibrate. Now, if you take out the vibrational entropy from the total entropy of the system, then you will kind of get a count of this number of minimas in the system. So that is what is a configurational entropy. And the relaxation time is usually there's a well-known Adam-Guest relationship which says the relaxation time follows this configurational entropy of the system. So somehow the system knows when there is a larger configuration space that the system will try to relax faster. It's like it knows that there is more phase space available to it. When the configurational space is small, then the system cannot relax. So there is because it doesn't have enough space available to it to move around. Now, this configurational entropy had been calculated long back in 1948. So the way it was calculated then was that it was depicted as delta S, that the liquid entropy minus the crystal entropy, assuming that the vibrational part of the entropy is given by the crystalline entropy of the system, is the configurational entropy. This delta S is same as SC here, and the TSC, if you plot, it was found that it follows a behavior like this. It's like if you plot it against T by Tk, it follows a linear slope, and at T equal to Tk, there is a extrapolated value of Tk where the configurational entropy appears to vanish. So the experiments stop here where the glass transition happens, because the experiments cannot continue beyond that temperature. But if you extrapolate it at this line, it appears that at T equal to Tk, the system entropy, the delta S or the SC is 0. That means the entropy of a liquid or a supercooled liquid becomes same as the entropy of the crystal. That means there are no phase space available to it, so it's only the vibrational entropy. Then if you think about it, there is something like an ideal glass transition. This is a conjecture, it has not been proved yet because doing experiments below Tg is very difficult. But if this is true, then there should be an ideal glass transition, like we have a crystalline minima, a unique minima in the phase space. It is then expected that there will be an ideal glass minima, and the system should undergo a second order phase transition. Why second order? Because in Ehrenfest way, there is nothing changed, no discontinuity in the entropy, in the volume of the system, in enthalpy. It is continuously going to 0 or disappearing. So that's the reason it's assumed to be a second order phase transition. Now, there is also another school of thought which is like it's called like depicting the glass transition as a random first order transition theory and transition, which says that there are mosaics in the system like these. There are domains, each domain behave in a different way, and there are multiple different structures which can be a glassy structure of the system, and there is a nucleation because you can always change from one structure to the other. So basically it's a nucleation to a new state, and it is an entropic, like it's not an enthalpy. In normal nucleation theory, it's the enthalpy which drives it. Here it's an entropy which drives it. And if you think about it, like, why is it there is no latent heat, although they are calling it as a first order transition, is that each domain will melt at a different temperature because the structure of each domain probably is different. So that means there will be a continuous change in energy and not a drastic change in energy at a particular temperature. This is what is this is the concept behind the random first order transition theory. And then there is also another theory which says that there is nothing thermodynamic in this, it's the slowing down of the dynamics and everything can be explained from a lattice model, and it is only the constraints. There is a less number of excitation possible at lower temperature. So there, like, because of this, there are more constraints in the system, and that is what gives rise to the slowing down of the system. So, there is like so much of puzzle, like if it is a first order transition, if it is a second order transition, if at all it's a thermodynamic transition, all these are question marks, and that's the reason it becomes very, like, it's still a very interesting subject to understand and try to understand what is happening in the system. Now, before I go further, let me try to give you a feel of the different transition temperatures in the system. So when I come from high temperature, the first transition temperature which we hit is the onset temperature. Now, at this temperature, this is similar as the melting temperature. That means below this temperature, the system gets into the supercooled liquid domain. Below that temperature, there is often a temperature called the mode coupling theory transition temperature, where certain properties of the dynamical properties of the system changes. We have done a lot of study on this, but today's talk I won't talk about much on this. Below that temperature is a glass transition temperature, which is probably the only temperature which can be experimentally measured, because it is just says that viscosity should be 10 to the power 13 Pascal. And below that temperature is the Kaufman temperature, or we also call it a VFT temperature. This is an extrapolated temperature where the extrapolated entropy would appear to go to 0. And because the entropy would go to 0, it is expected that the dynamics should diverge. So this is what, these are all the different transition temperatures in the supercooled liquid domain till it undergoes a glass transition. Now next, let me tell you what do I mean by structure, because the main topic in this work is structure. Now, what do I define by structure is something very simple. It is basically trying to look at, take a central particle, trying to look at the probability of finding other particles around it. Okay, and this can be obtained from a functional form like this, where Ri is the particle and Rj can be the other particles, and you sum over all the particles, and on an average you get a structure of the liquid, or structure of a gas, or a structure of a solid. Now, a gas does not have any structure. A liquid has a well-defined structure where there are particles, there is a higher probability of particles in a certain range, and then within a certain range there is a lowering of probability of particles, then there is an increase in probability of particle in another range. And in the liquid state theory, if you know the structure, you can calculate the pressure, energy, compressibility, potential of mean force, dynamics, everything. So in the liquid state theory, structure plays a very big role in understanding the whole system, and so that's the reason a lot of importance is given to structure. In the solid also, the structure is very well defined, and that can describe the mechanical properties. Like, if you have an FCC crystal versus an SC crystal, these peaks will come at different places, and the mechanical properties and everything can be described in terms of the structure. The Fourier transform of this structure in real space is nothing but what you get from X-ray diffraction. It is called the structure factor. So when I talk about structure, I will I will change between GR and SQ, which is the wave numbers plane of this same function like GR, and they provide you very similar information of the system. So this is basically what is structure, and how does the structure of a supercooled liquid look? So if this is a colloidal system, you will see that, it looks very disorganized. It's an amorphous system, right? You wouldn't expect the structure to be very organized, unlike that in a crystal. And here is another system which is in an amorphous state, and its crystalline structure looks like this. So structurally, a glass or a supercooled liquid will behave very similar in a very similar way as a liquid, whereas in the mechanical properties of the system will behave more like a solid or a crystal. So so this has a very mixed characteristics of, it's neither a liquid nor it's like a solid. It has part of the solids properties and part of a liquid like property in the system. Now, what I'm going to do today is I'm going to talk about how structure via entropy can determine the dynamics, how structure via a softness parameter, which I'll define what it is, can determine the dynamics, and how the local structure and the local dynamics are connected. So there are kind of three problems, and all these three problems, I'll say why it was initially thought that it cannot explain anything, but we can do it now. Now, what happens is the structure of a liquid changes continuously. There is no discontinuous change across the onset temperature till a very low temperature, whereas the dynamics changes orders of magnitude. So then there are lot of these liquid states theories which uses the structure to describe the dynamics, and the question was asked, can any theory describe the dynamics of a supercooled liquid, because the structure hardly shows any change, whereas the dynamics shows so much of change. Further, it was found that two systems, one an attractive Lennard-Jones potential and a repulsive WCA potential, both of them have very similar structure at high temperature and at low temperature. These are all scale temperatures of the system. Whereas when it comes to the dynamics of these two systems are very similar at high temperature, but they become order of magnitude different at lower temperature. So then immediately this group in France concluded that, started asking questions first, that can structure determine the dynamics of the system? Because if two systems have very similar structure but different dynamics, then the first thing probably expected it is can't. So they did some tests, they applied this structure to a theory called mode coupling theory. They used it to also a density functional theory. They calculated the dynamics from there, and they found that the dynamics given by the system, this is a relaxation time plotted against inverse temperature, while they are so much apart in the real case in the simulation studies, they appeared to be very close in that predicted by the theory. So this clearly and they ran other liquid state theories, and they said no, structure cannot determine the dynamics. So this was a conclusion in 2011. They did a series of tests, series of work, and then they said that in supercooled liquid, structure cannot play any role in determining any of its properties. Now, what is the consequence of this? As I told you, in the liquid state theory, the thermodynamic properties can be obtained from the structure. Now, if structure cannot determine the dynamics, that means there is a question that is are the supercooled liquid properties, is there an underlying thermodynamics which is driving, or there is no thermodynamics, it's only a kinetically constrained system? That's the question mark. Like, is it thermodynamically driven, or there is no thermodynamics behind the slowing down of the system at that low temperature? So first we said, okay, let's try to understand that. When we calculated the entropy of the system, the entropy is calculated, the total entropy is calculated by using a thermodynamic integration method. I won't go into the details of the technique, which we can always discuss later. And then we subtract the vibrational motion from there, and we get a configurational entropy. And this configurational entropy, as I told you, is the count of minimas here. And we found that the configurational entropy of the systems, the two systems that had very similar structure, are quite apart. So, okay, it appeared then that there is a difference in the thermodynamics of the system. All the structure appears to be very similar. Then we found that not only the thermodynamics is different, the dynamics can be explained through the difference in the dynamics can be explained through the difference in the thermodynamics of the system, because we plotted this Adam-Gibbs relationship, and we found that Adam-Gibbs relationship holds in the system. So then we said, okay, it is now proven. First thing what we could prove is that although it appears that structure does not play a role in the dynamics, but thermodynamics does play a role in the dynamics. Now, what we haven't done here is we haven't said if it is a pair correlation which is affecting, which I call structure, affecting the thermodynamics, or higher order correlation. Now, What do we mean when we calculate entropy as pair and higher order? Is there some way to understand it? Now, as I told you, the total entropy is calculated as a part of ideal gas entropy plus that excess entropy of the system. What is excess entropy of the system? It is a lot. So the ideal gas entropy is the maximum entropy a system can have. That means there is no interaction in the system. Depending on the temperature, the momentum is described and the whole volume is accessible to all the particles. Now, because of the correlation between the particles, because of an interaction potential, the excess entropy, which comes usually in negative, lowers the total entropy of the system, and this excess entropy is usually calculated from the total interaction potential of the system. However, the excess entropy can also be calculated in terms of the role of two-body interactions, the role of three-body interactions, and role of higher-order interactions. What I mean by two-body, three-body, and higher-order interaction is when two particles interact directly with each other, that is called a two-body interaction. When a particle, say 1, interacts with the particle 2 via a particle 3, then it's a three-body interaction, and then if it interacts via 2 more particles, then it's a four-body interaction, and so on and so forth. So basically what we did was we said, okay, we will separate out the two-body part and the higher order part and try to look at the role of the two-body interaction in the entropy. Now what we did was, this two-body interaction can be explained because it's two-body in nature. It can be explained in terms of the radial distribution function, which is the structure of the liquid. And we found that two systems which have very similar structure, surprisingly, have very different two-body part of the configurational entropy. So that means what we figured out is a small difference in structure is good enough to provide you a large difference in the configurational entropy of the system. Now, not only that, we also showed that the dynamics would have diverged at a much higher temperature if the interactions were only two-body in nature. Now, this was something which was very puzzling because in the supercooled liquid community, it is believed that as you go to lower and lower temperature, and because of the correlation between different particles, the system slows down. So then it was surprising when we found that when we have only two-body correlation, the dynamics diverges, whereas when we have higher order correlation, the dynamics does not diverge. This is all coming via entropy. And so to understand that, we tried to understand the role of pair and higher order entropy in the system. What we found is that if we plot, these are for two different systems, if we plot the pair and higher order entropy, then at higher temperature, the pair entropy is higher than the total entropy of the system. So X has the total entropy, which is the delta S, and plus S2, whereas S2 is plotted here by the open circles. So the open circles have higher value. They are all negative value because there's a loss of entropy. But loss of entropy is less by two-body interaction, whereas loss of entropy increases when you have higher order interaction. However, below a certain temperature, there is a switch happening, and loss of entropy is more when you have a two-body interaction, whereas loss of entropy is less when you have higher order interaction. And this delta S, which is the higher order correlation, undergoes a change of sign. It is initially negative at higher temperature and goes over to a positive value. So what we figured out is that at low temperature, many particles together, correlated motions, allows an activated motion, and this increases, this helps the system to explore higher phase space. So that there are these configurational space which it couldn't have explored via just having two-body interaction, which it could explore when there were higher order interactions. Now, this is something which can be understood in a very physical way by looking at a crowded bus, which many of us who lived in Kolkata knows what it means. When the bus is less crowded, all you have to do is tell your neighbor, can you move a little, and you can come out of the gate. But when the bus is really crowded and your neighbor moving wouldn't allow you to come out of the gate, you have to tell your neighbor to speak to his or her neighbor to move, and together many people can move for you to come out from the bus. So it is like a correlated motion of many particles which will allow you to explore a different part of the phase space. So this is something very similar concept to that. Now, what we also showed is that all the all the three transition temperatures which I told you, which we couldn't measure in experiments, they have all a thermodynamic origin. So two entropies cross at this temperature. From below this temperature, the delta S becomes positive below the onset temperature. Then we found some that, anyway, configurational entropy was found to go to 0 at Tk. We found the pair part of the configurational entropy goes to 0 at Tk2, which is the mode coupling theory transition temperature. So we had been working on the role of pair structure in thermodynamics and the dynamics of the system, and it was published then in a series of paper on this. So it started from 2014 to 2017. Now, while we were working on this, I think the community, the glass community, started rethinking about the role of structure in the dynamics, which they earlier thought was not there. So what they found, so the role of structure was revisited, and this is by a group called Simmons collaboration, and under cracking the glass problem. So they went to, there is a project called cracking the glass problem. In that, there are very high profile people working there both in the US and Europe, and they said, quoting our paper, that although it is unclear why the configurational entropy should play a role in the temperatures studied which are above the mode coupling theory transition temperature, these results suggest that the relationship between GR and dynamics should be revisited. Now, what they did was they used a machine learning technique to revisit to understand the role of structure in the dynamics, and this machine learning technique was earlier published in a Nature Physics paper. The technique says what they do is they identify particles which are mobile at a particular snapshot, and they then identify 160 structure functions around each particle. So the structure functions are probably at a distance say x, x1, x2, x3, like that, 160 of them away from a central particle. Then they look at how these structure functions are and what is the probability of the particle to be mobile. Now, they train about 6,000 such sets of mobile particles, the particles which are mobile and particles which are not mobile, and study their structure functions. With that, they create a hyperplane of these m vectors, and the distance from the hyperplane is what they use as a weighting function, and they weight the structure function GR by this function W, and they calculate a softness parameter, which they name as a softness parameter, and they show that the softness parameter of those two systems which had very similar structure were different, and if the relaxation time was plotted against the softness parameter, then it appears that the softness can describe the relaxation time. So what they said is, okay, the softness somehow has the information of the structure in it. They do not know how, but this softness can then describe the dynamics of the system. Now, the question here is, what is this weight function which is not known? It's like a black box, right? You get a weight function from the machine learning. You do not know how the machine has learned about this mobile and immobile particles and how they brought out the weight function. What is its connection with the structure of a liquid? It was not known. Now, during this time, we had already developed a mean field theory. This theory was meant, it is like an Ising model. Now, if you want to look at the mobility of a particle, short time mobility of a particle, now you have to understand its interaction with all other particles, and this all other particles can also have a mobility of their own. Now, like Ising model, we decided that, okay, we will not consider the mobility of the other particles. We will take this particle and assume the background to be a frozen background, and this will be an homogeneous background for every particle, and this particle would feel this background potential, which we describe in terms of the structure of a liquid. We could describe it. It is microscopically derived through a Ramakrishna-Yusuf free energy functional, and we reach this functional form of the potential, which looks like this. It has a minima, and then it disappears at a larger R. Now, we said, okay, we can always calculate the softness of the potential, because this potential is the caging of every particle, like it's a potential which every particle, assuming there is a homogeneity in the system, every particle feels, and then there is a softness of this caging potential, which is basically the curvature at 0, which is basically going to tell you how strongly the particle is going to be stuck in that minima, which is created by the cage of the other particles around it, assuming the cage is static. Now, this is something very important, that we have assumed that the cage to be static. Now, what we found is that the softness actually shows a linear temperature dependence for many systems. Here there are systems WC and LJ, which is a repulsive and attractive potential at different densities. We have also gone to active systems, so which means we have also gone to out of equilibrium systems, but we found that this property doesn't change. The softness shows a linear dependence, but the slope is different. Now, what we also found is that when for those two systems where the structure looked very similar but the dynamics was different, we found that the dynamics in terms of the softness, you can make plots like this, like the machine learning study, which will appear that if you can describe the softness of this mean field caging potential, then it can describe the dynamics of the system. However, the moment we plotted it for a larger number of systems, we found that no, it no more can describe the dynamics. There is some kind of a system dependence. Now, to understand this, what we said is, okay, we have this all different relaxation times, which has a wide range of temperature dependence, like the whole set of systems that we studied. We said, let's assume that we write it in terms of an Arrhenius equation. But you remind, I want to tell you all that delta E is not a temperature independent function, because if it was temperature independent, then it would have been a straight line like this for a particular system. But because it's a temperature dependent function, you will see that tau versus 1 by t is no more a straight line, it shows a parabolic curve, which means it grows sharp faster because the delta E grows with temperature. Now, what we said is, okay, let's plot this delta E obtained from the simulated relaxation time versus the softness that we calculate from the structure of a liquid. And we found that for all the systems, this delta E shows a linear behavior with this softness, but the proportionality constants are strongly system dependent. So we said, okay, we can write the delta E in terms of this kind of a functional form where C prime and B prime are system dependent. And we say that the temperature dependence of the activation energy is actually related to the temperature dependence of the local softness parameter, which is of course calculated at an average level. As you can see that I've considered a homogeneous system, a homogeneous liquid, I've calculated an average quantity, but we got an average value of the softness, we have an average value of the relaxation time, and we could show that the delta E has this connection. Now, if I put together these things and I will say, okay, tau alpha should go like this, where delta E has a dependence on the softness, then I can write the tau alpha in terms of the softness parameter of the liquid. And now when I plot the tau alpha against the softness with the system dependent parameters, I can see a master plot. That means the softness indeed can describe the dynamics of the system, but the role the softness plays in describing the dynamics is very system dependent. The C prime and the B prime decides how strongly the softness can describe the dynamics. For certain systems, it can describe it very strongly, in certain other systems, it can't. Now, this is what was published in this paper. Now, I'm going to change gear and go to the last part of my talk, where I try to understand the origin of the dynamic heterogeneity. Now, where does it come? I had shown you that, we have a fast moving regime, we have slow regime. These were experimental results, and people try to always understand why in the supercooled liquid this heterogeneity comes up in the system. Is there a structural origin to it? That was always a question. Now, certain studies have shown that if you calculate the vibrational entropy of the system, then the regions which has a low frequency vibrational modes shows a higher propensity to move. Now, there has been overlap of these regions shown in this 2008 Nature Physics paper, and this was supposed to be a big achievement that, okay, we have started seeing properties which are heterogeneous in the system, but we haven't yet seen something which is related to the structure. Now, recently, there has been also another experimental work which showed that the softness which is obtained from the machine learning studies can tell you where the dynamics of the system is faster, which undergoes, it's like a supercooled liquid or a vitrified liquid, which undergoes a crystallization. Because the moment a region can have larger motions and larger displacements, it would probably like to undergo a crystallization, which you could avoid by fast cooling the liquid. So the domains which were soft and where the dynamics was faster underwent a crystallization process. This was shown in this paper, which also was published in Nature Physics. Now, the softness parameter was again calculated using machine learning, but as I told you that the machine learning studies cannot directly connect it to the structure, It is basically going to tell you that there is some weight function, we do not know how that weight function is. So, is there a correlation with structure? Now, if you think about it, this whole connection between structure and heterogeneity came from the defects, from the idea that in solids, defects leads to dislocation. There can be different kinds of defects, and the defects can lead to the dislocation. So that means the mobility of a region is more where there is defect in the system. Now, in a crystal, it is possible to understand defects because the structure is so well defined. Is it possible to understand a defect in this kind of a system? Which one is a structure and which one do you call defect? It is really a challenge to understand defect. So what we are now trying to do is we are trying to understand the structure now, not at a global level, not the overall structure of the liquid, but the structure around each particle. And we are trying to say that the structure has a heterogeneity. If it has a heterogeneity, can we describe a structural function which can actually find out this, which can detect this heterogeneity? Now, we earlier showed that the softness parameters or the mean field potential that we have described can describe the softness, and the softness was connected to the dynamics. But now that was done at a global level, whereas at local level there can be fluctuations both in dynamics and structure. And it is well known that correlations between average quantities does not guarantee a correlation at a microscopic level. So I'm now trying to look at a causal relationship between a local structure and the dynamics at a microscopic level at each particle level. And we took a leap of faith and we said, okay, let's try to extend our theory. It means use the theory but work it. It's a liquid state theory which talks about a homogeneous liquid, but we said, okay, we will use the theory, we will try to modify it to now try to understand the local structures. I wouldn't go into the details of it, but we can always discuss about it. But we did figure out a way of describing the local structure in terms of the radial distribution function and a direct correlation function, which also only depends on the interaction potential of the system. And the most interesting result that we found is we found a distribution of this softness parameter. That means when we calculated the softness, we found that the softness has a distribution, and we found that this heterogeneity actually increases as you go to lower and lower temperature. And also what we found was that if we calculated the lifetime of the softness, we found that the softness also shows kind of two-step relaxation, and this lifetime of the softness was connected to the cage structure of the liquid. That means as long as there is a cage structure, the softness is long lived. So softness, the lifetime of the softness was connected to the cage structure. Here is a function overlap. Here is basically the dynamical function which I had plotted earlier, and here is the correlation of the softness, and they seem to have a similar lifetime. So now I have a structural heterogeneity. I find the structural heterogeneity to be long lived. So this appears to be a very good candidate for understanding my dynamical heterogeneity. Now, so what we do is now, next step is we now try to connect the structure to the dynamics. Okay, so before that, what we also plotted was that if we look at a structure of a particle, the softness of a particle, and which a particle which is not moving, but maybe its neighbors are moving, can that affect the softness? And we found that the softness can be affected even for those particles. That means what appears is that a regime which is a hard, means which is in a very deep minima, can come out of the deep minima because of the mobility of the regions around it, maybe not its immediate neighbor. And this is the same thing which has been also found in the machine learning studies. So I'm going to now plot many of the results, what we find and what is shown in the ML study. The ML study starts with the hard particles with a negative softness, so that's the reason you see it is coming from this direction, whereas we get it from this direction, but it's a similar result. The values of the softness are different, but the results are very similar. Now, what we did was we tried to calculate a fraction of a particle. So we took the softness of uh, all particles which has a certain value of softness. From there, we figure out which are the particles which are fast, which are slow, and we calculated the fraction, that is the PR, and we found that at high temperature, the softness does not describe too much if the particle is going to move or if it shouldn't move. The fraction remains almost the same. But as we go to lower temperature, the particles which are higher, S value is high, which means which has a higher value of softness. Higher value of softness means the local cage is probably flatter, has a higher probability to move compared to a particle which has a lower value of softness. Now, this is again similar to what has been obtained from the machine in the machine learning studies. And the reason is at lower temperature, the softness becomes a better detector of the dynamics because the softness is well defined, because the cage around a particle has a long lifetime, and if there is a long lifetime of the cage, then the softness has a meaning. If the cage itself doesn't have a long lifetime, then the softness parameter cannot have any meaning. So this is what was the what we figured out from this work. And then what we said is, okay, can we now write this probability in terms of an Arrhenius equation, where we said that the energy is dependent on the softness. What we find is, yes, these are different values of different colors are different values of softness at different temperatures, and we found that they all behave in a same, like you can write it in this kind of a form, and the slope, the higher the value of the lower the value of softness, that means more hard the particle is surrounding, the stronger is it.
There is a question.
Yes.
Hijab, please go ahead.
No, no. I will ask towards the end of the topic. I mean, I
Okay.
just sorry. Yeah.
Okay, sure.
Okay.
Okay.
So then this shows that the slope is higher when the softness is less. That means a hard particle has a stronger temperature dependence, whereas a soft particle doesn't need that much of a temperature dependence. It can move at like its probability of motion is a little less dependent on temperature. And all these plots cut at a point which is around the temperature T is equal to 0.8. This is also very similar to what the machine learning study has found. Now, machine learning study has reported that there is a crossover at this temperature, and above this crossover, as you can see, that the probability of a particle which is hard is probability of movement is higher, which is an unphysical result, which tells us that below this temperature only this correlation between softness and the dynamics is valid. Above this temperature, it will not be valid. Now, why this temperature is important? This is something which we can understand from our theory. And what I'm going to tell you is, so I had shown you all these temperatures, and this T is equal to 0.8 is something near the onset temperature. Now, near the onset temperature, we found that this intermittent dynamic starts, and the system starts having this decoupling between the fast and the slow dynamics. That means the moment you have a decoupling between fast and slow dynamics, only then you can start seeing a cage. Otherwise, the movement of the cage and the vibrational motion of the particles are all merged in the same time scale, and you do not have a well-defined cage. You cannot describe a well-defined structure, the softness of the cage, and that is precisely the reason both the ML study and our microscopic theory predicted that around only below that temperature the softness can become a predictor of the dynamics, and as you go to lower and lower temperatures, the softness becomes a better predictor of the dynamics. Now, what we also found is that this delta E, which I showed you, is basically replotting like the information from that plot in another graph, that the energy barrier depends on softness. The lower the softness value, the higher is the energy barrier. So it takes a longer time for the system to move. That means this temperature dependence is stronger. Now, what we have shown here now is that structural heterogeneity increases at lower temperature, and structural heterogeneity is longer lived at lower temperature. So these two combined tells us the structural heterogeneity drives the dynamical heterogeneity of the system. So what we feel is now we could actually describe the origin of the dynamical heterogeneity in times of a structural heterogeneity in the system. So it's first the structural heterogeneity which comes up, and that determines the dynamic. It's a causal relationship. Now, why do we need a microscopic study when we have a machine learning technique? Is something, a question which is a very broad question. I wanted the audience, I wanted to let the audience know what are the importance of microscopic theories. See, first of all, we don't need any training set. So how we train the system, it doesn't matter. It's a theory which gives exact result even for a single particle. Now, it directly connects to the structure, which the machine learning study couldn't. Now, because it couldn't, machine learning study could only leave at this S versus tau. The moment it would have gone for larger number of systems, it would have found that this doesn't follow, and it wouldn't have known what to do with it. Whereas because we were working with a microscopic theory, we knew what is the relationship, why there is a relationship between the relaxation time. This is kind of a ln of the relaxation time and the softness, and we could predict a formula like this, that this is a correlation between the softness and the relaxation time, and the C prime and B prime parameter can be system dependent. Also, what we could do is we could actually describe a cage. We could show that this lifetime of a cage has a correlation with the lifetime of the softness, and that brought out the picture clearly, that is precisely the reason the dynamical heterogeneity becomes more at lower temperature when the softness starts predicting the dynamics much more, because at higher temperature, the softness, when I say high, I mean even below onset, but there is a high and low regime. So in the high temperature regime, as you remember from one of the plots, the softness does not predict the dynamics so much, but as you go to lower and lower temperatures, the softness becomes a predictor of the dynamics because the cage is longer lived. Now, this work is just the beginning, because what we find is that the softness parameter now can have a big, it can play a big role in many properties of the system. First of all, we need to find out how much it is system dependent. Then we want to study the softness with the local mechanical properties of the system. We are already working with Andrea Liu. After a paper came out, Andrea Liu wrote to us that, can you now try to understand the correlation of your softness parameter and the machine learning one. So basically, we are doing particle to particle calculation of our softness parameter and trying to see what the machine learning has shown, to see if there is really a microscopic theory behind the weight factor that the machine is throwing out. It is just throwing out a weight factor, but is there a microscopic origin to it? And then this softness can actually there has been some studies showing that the brittle particles, if a ductile and a brittle glass can have different levels of this mobility, and also enhance subpicosecond relaxations are found to be important for polymeric glasses. And on all these cases, the softness parameter will play a big role, and we believe, since it's a microscopic theory, we will be able to understand many things much better than we do from the machine learning studies or the vibrational mode studies, actually. With that, I would like to thank you for your attention.
Thanks, Sarika, for this very nice talk. I already see Vijay has raised. Vijay, please go ahead. Unmute yourself and please ask the question.
Yeah, thanks, Sarika, for a nice talk.
Thanks, Vijay. Yeah.
Yeah. The question that I had was first you computed the softness for the entire system. There
Right.
you did sort of mean field theory, to
Yes.
get average, the potential that a given particle sees. Okay.
Right.
Now, when you go to the local level, what is it that you changed? Can you explain a little bit?
Yeah. So I went through that part quickly because I thought I will ask, I'll tell it when there is a question. So what we usually do is we calculate it in terms of the structure factor, which is the Fourier transform of the radial distribution function. Now, calculating the structure factor at a single particle level is not possible. It's very it's a fluctuating function which you cannot describe. So what we did was we first described everything in terms of we converted it in terms of the radial distribution function, and then we did something. We kind of even the radial distribution function at the single particle level are sharp. They are basically histograms, but there is a way that if you can take into consideration the small vibrational motion of the particles, then you can actually, oh sorry, I don't know how it I'll connect it back. You can, okay, so then this radial distribution function actually can be obtained, which I haven't put this in the slide here, in terms of a Gaussian sum over Gaussians, which makes it a continuous function which is integrable, because we need to integrate this function. So we cannot work with histograms like that. We needed something which is a smooth function, and we did manage to obtain the smooth function. But there was always a question mark that, with this way, will it really show a local property of the system? But we found that yes, it can show a local property. So that's the reason I said we took a leap of faith, because liquid state theories are all mostly done for average properties of the system, but I guess this is the first time we extended a liquid state theory thing to a local property. Before this, the two-body entropy was calculated at a local level, but which did not show much promising result, but this structure does actually, So this is what it is, but the other details of how we do the G, alpha, beta, R, and all those things, which we can always discuss.
Okay. Yeah, thanks. And what is the C alpha beta? This is just the interaction potential between two particles?
No. So it's a direct correlation function which is dependent on the interaction potential under certain approximation and the radial distribution function. So ideally what we need now is, we need the count of number of particles, we need this histogram, we put a Gaussian around these histograms because we assume that there is small vibrational motion of the particles, so they are not sharp positions, and we also, all we need is the interaction potential between particles, and together we can describe the softness, the caging potential or the depth of the caging potential, and inverse of that is related to the softness of the particle.
And these alpha betas, like, do you average over the nearest neighbors to get this?
Yes. So we average over the nearest neighbors, and it depends. Right now we do over the first nearest neighbors, but this is a theory, and we are still working on it, how to improve it further. So we have found that the first nearest neighbors are the ones which shows the most dominant contribution in describing the softness of the particle. And we are actually seeing a lot of correlation with the machine learning softness because we share data and it shows a lot of correlation actually.
Yes. So this alpha beta, are these particle indices, or these are
Sorry. So these are they are species indices. So
species
if you have a
indices.
polydisperse system, there can be multiple species. Here we were working on a binary system, so it has AB system. So these are basically trying to look at the species relation of the alpha beta.
Okay, fine. Yeah, thanks. Yeah.
Any other question?
I'm done, I would say. Thanks a lot.
Yeah, you're welcome.
Any other question from anybody else? Okay, Sarika, I have a very naive question. I don't know almost anything about this field, if I worked on this and all that. So, when you introduce this aspect or quantity softness, what does it do to the difference between the particle timescale and the cage timescale? I mean, what can I say? If a system is softer, does that mean these timescales are more well separated?
No. So the softness will not tell you about the time scale, but the temperature will tell you about the difference in time scale. So what happens is, at a particular temperature, you have a certain decoupling between your fast and slow dynamics. So the wider you have a decoupling, the more well defined the cage would be, because vibrational motion within the cage and the cage relaxation usually at high temperature happens at the same time scale. You cannot really separate it out. So you do not see a well defined cage, and you cannot have a well defined caging potential and its softness. But as you go to lower and lower temperature, this cage becomes more well defined because the structural relaxation of the cage slows down. So what you can do then is, you can actually describe at a particular point where the particle is caged, that what is the softness parameter it has, and then it will tell you that what is the probability of it then coming out of the cage. So I think the information of a cage being well defined is extremely important for the softness to be described. And when I describe the mean field theory, I said that I assume the background to be frozen. Right. So that means I had considered there is a cage. Now, this theory is better suited as I go to lower temperature, and that's the reason I find softness to be a better predictor of the dynamics. So these are the things which we can understand because we came from the mean field theory. What happened is, machine learning, they reported these things, without really being able to go back and say why the softness becomes a better predictor of the dynamics at a lower temperature versus like at a higher temperature. Like they observe the same results without the knowledge that why a cage can become like there should be a decoupling between dynamics and the cage should be well defined. Only then the softness can become a better predictor of the dynamics.
Okay, at a more intuitive level, I mean, suppose given that the cage is well defined, I am in that regime. So, at an intuitively speaking, when I say the softness is increasing, what does that mean? That the particle can now actually sometimes go out of the cage or something like that?
No, no. So the cage is ill-defined, but the cage is less structured. So the cage is well-defined, but the cage is less structured. We have actually calculated the radial distribution function of particles which are soft and which are hard. And we found that particles which are soft have a much broader cage. That means the particles around it are more distributed, whereas particles which are hard, the cage means the particles around it are very well defined. So it is holding on to the central particle strongly, whereas particles which are soft have a very ill-defined, like the cage is less defined. Now, we never expected a theory to really find out this small differences in the structure and give a number out, which can then finally predict the dynamics. So the fact that we could get a heterogeneity in the softness itself was like, so basically there were small differences in the cage structure, which the theory could pick up.
So, you
And
are
then it
saying
could,
that as softness increases, the cage becomes more fuzzy
yes,
instead of a
yes,
very hard, rigid. Yeah, okay.
yeah. So basically, if you look at a particle, there might be the GR is sharper when all the particles are all sitting probably all touching the central particle. Whereas the GR can become a wider GR when some particles are little far, some are touching. So basically, there's no well-defined cage. So the less defined the cage is, the softer is the softness parameter of the system,
Yeah, I
of the
understand.
particle.
Thanks.
Sarika,
Yes, Ranjita. Yeah.
uh, uh, in your theory, is it that the dynamical heterogeneity requires structural heterogeneity, right? Structural heterogeneity is the prerequisite for dynamic heterogeneity.
That's what the theory is predicting, and that's what the work is predicting. So what
Okay,
happens is in the theory, I calculate the dynamic heterogeneity independent. So basically, I don't calculate the dynamic heterogeneity from the theory. I calculate it from the simulation,
okay,
and I calculate the structural quantity also from the simulation, and then put it into the theory to calculate the structural heterogeneity. And
okay.
then I see that the structural heterogeneity has a correlation with the dynamic heterogeneity.
Okay, so it's kind of structural heterogeneity is related to dynamic heterogeneity, at least for the temperature regime that you are working. My
Yeah,
question is whether this is also true for systems which are showing appreciable amount of dynamic heterogeneity at temperatures 100, 150 Kelvin above their thermodynamic glass transition temperature.
so
So,
I do not know about those systems, but definitely you must be aware of them, and it would be interesting to see that if there is a structural heterogeneity in those systems too.
right. So my question is like this: that whether the dynamic heterogeneity we see in deeply supercooled systems near glass transition,
Hmm.
the origin there is different or the same for systems which are showing dynamic heterogeneity, which are much above the thermodynamic glass transition temperature.
So that would be something interesting to look at actually. If you are aware of some system where it can
Yeah,
be applied.
there are, and
Hmm.
these systems are not polymers. These
Hmm.
systems are small molecules,
Hmm.
but they are kind of different systems prepared differently, kind of
Hmm.
metastable systems, but this metastability is not at a very low temperature. It's rather high temperature, avoiding crystallizations through interactions. Okay,
Okay,
I'll
because
discuss it.
normally it is expected that at high temperature a liquid is homogeneous.
Yeah,
So
it's
if
not. It's
yeah,
not.
so if there is a heterogeneity, probably there is a structural role to play, or it has a different role to play. It would be something interesting to look at.
Yeah. So since your theory has this single particle level, rather more local level theory, so this really gives the appropriate microscope to look at what is the origin of such dynamic heterogeneity.
Yeah, that's
connecting the microscopic dynamics to the macroscopic observations, because there also the Stokes-Einstein relationship is severely violated, even at that high temperature. So you measure them, and then you bring back to that understanding to find out the microscopic origin, and your theory could be applied.
Yeah, that would be great. Yeah, we should look at it actually.
Right.
Yeah.
Thank you.
Thank you.
Any other questions from any of the students?
Yeah, I thought the students will have more questions, but probably, I guess, soft condensed matter is something we need to now introduce in the master's level for students to appreciate what is taught, what we work on actually.
Yeah. It seems there is no other question. Okay. Then thank you, Sarika, once again for the very nice talk. And,
thank you.
We hope to invite you sometime to our center.
Yeah, in person, right?
Yeah, that's something I'm looking forward to too. Actually, yeah, definitely. Yes.
Okay.
Thank
you.
Thank you.
Bye bye. Yeah.
Bye.
Bye.
Bye.